Now we're going to start Chapter 10, Part 1, Energy. Energy is the ability to do work or produce heat. And the big thing about energy is that it's always constant, meaning we cannot create or destroy energy. The total amount of energy in the universe is constant. We are only transferring between different types, such as potential to kinetic. Now, what's very important is that we do not mix up temperature and heat. So temperature is the measurement of the random motion of those molecules. So the faster those molecules are moving, the higher the temperature. Heat is the flow of energy between two different objects. So on the left side here, we have hot water and cold water. And on the right, we have the equilibrium with the two waters being the same temperature. So here we had energy flow from the hot to the cold. And then over here we have the equilibrium temperature where both sides are the same. Once again, energy cannot be destroyed, it is only transferred. So we transferred energy from the hot side to the cold side until both were at the same temperature. Just like in math, when we set up our axes to determine our origin, we need to set up how we are going to look at our energy and which way it is going to flow. So we set up two things. We have the system, which is the part that we care about, and then everything else is the surroundings. So for us, we usually care about the reaction or process, then everything else is the surroundings. Is energy leaving or entering our system? And that's going to determine our sign. In an endothermic process, heat is going to flow into our system. And where does that energy come from? It comes from the surroundings. In an exothermic process, energy is going to flow out of the system. And where does that energy flow to? It flows into the surroundings. Now, if we were to add up the system and surroundings, it's always going to equal the universe and be constant. What the system loses is what the surroundings gain. Thermodynamics is specific to the study of energy and in our chemistry. How does a reaction transfer energy? So we need to know three things here. We need to know the amount of our substance, so how much water are we going to heat, how much methane is going to combust. We also have to measure the temperature change. So we just use a thermometer and we have our initial temperature and we have our final, and just final minus initial, we get our change of temperature. And we also have to know our substance, because each substance has what's called a specific heat capacity, and that's the energy required to change the temperature of a mass of 1 gram of a substance by 1 degree Celsius. How much energy does it take to change the temperature of that object? So here's a table of specific heat capacities from common substances. So water, 4.184 joules per gram degree Celsius, which that is the standard unit for specific heat capacity. That requires a lot of energy to take that liquid water and get it to warm up. That's why it takes so long for water to boil. Or if we look all the way down at mercury and gold, it doesn't take that much energy for it to get warm. This is why we use such as aluminum in our cooking, because we want that pan to get hot. We put energy from our stove into the pan in order to cook. And we don't want to waste that energy on trying to warm up the pan. We want it to get hot fast. So here's an example of a reaction. Sulfur plus oxygen gives us sulfur dioxide. And we're told that the enthalpy, or the energy released, is negative 296 kilojoules per mole of SO2 formed, meaning we will release, or it's an exothermic process, 296 kilojoules when we form 1 mole of SO2. So we need to calculate the amount of heat released when 2.10 grams of sulfur is burned. So starting off, when 1 mole of SO2 is formed, negative 296 kilojoules of energy is released. The negative signifies it's an exothermic process, and we have 2.10 grams. So our first step is to calculate how many moles of sulfur we have. So 2.10 divided by 3.206, which is the molar mass of sulfur, gives us 0.0655 moles of sulfur. And then now we need to figure out how many moles of SO2. So we use our ratio, which came from our balanced equation, to determine how many moles of sulfur dioxide. Now because it's 1:1, we form 0.0655 moles of sulfur dioxide. And we know that in 1 mole of SO2, it releases, so it's negative 296 kilojoules of energy. So we actually released negative 19.4 kilojoules from 2.10 grams of sulfur. So this is a very similar problem to the last one. We have 5 grams of propane, and we're given an enthalpy of negative 2,221 kilojoules per mole. So our first step is to take our 5 grams and convert it to moles using the molar mass. And then we know that we have negative 2,221 kilojoules per mole of propane. So if 5 grams of propane is burned, we release negative 252 kilojoules. The continuation of Chapter 10, Energy, Part 2. So Hess's law means that the enthalpy change for one reaction can be the sum of the individual reaction's steps. So this is very similar to you taking different routes to school. In the end, you're still going to get to school, but you can take multiple different routes to get there. So here, the overall reaction is N2 plus 2O2 yields 2 NO2. But this reaction being carried out in 2 steps. And each one of these steps has an enthalpy. Enthalpy 2 subscript 2 and enthalpy subscript 3. When we add these 2 reactions, we get the overall enthalpy of 68 kilojoules. Now we notice because in the first reaction, it produces 2 nitrogen monoxides. The second reaction consumes those 2 nitrogen monoxides, so they cancel out. You can think about that arrow as an equal sign. So if we have something on the right side that's the same as something on the left side, they can cancel out. Now, one thing to keep in mind, though, is that when we manipulate a reaction, we also need to be able to change the sign. So if we flip the arrow on a reaction, we're going to change the sign on the delta H. And that delta H is proportional to the amount of product or reactant we form or consume. The more product we make, the greater the delta H, either negative or positive. So here we are given 2 reactions, 1 and 2. And when these 2 reactions are manipulated and added properly, we're going to get the total reaction down here. And by doing that, we add the energies to get the energy for the N2 plus water to get oxygen and ammonia. So how we do this is we first work backwards. We look at the equation that we want to get to, so the N2 plus water, and we see how can we manipulate the first 2 equations in order to get that final equation. And we can do that in 2 ways. We can either reverse any reactions, so we take the reactants to products, or we multiply the reaction by a whole number, because we want our coefficients to match. Now by reversing the reaction, we not only just flip the arrow, but we're going to flip the sign on our energy. So in blue there, those are our original reactions, and our desired reaction is at the bottom. So the first thing we notice is that nitrogen is a reactant, and in our original equation, nitrogen is a product. Now don't worry about the coefficients yet, we just want to get the reactants on the correct side and the products on the correct side. So since nitrogen is the product in the original and we need a reactant, we flip it. So now we flip that reaction and our delta H is now negative instead of positive. Same thing for the hydrogen plus oxygen. We started out with water as a product, but we need it as a reactant. So we flip it and we flip the sign. Once we get our reactants and products on the correct side, now we can multiply in order to get our coefficients to match. So we look at nitrogen, and here in nitrogen, the coefficient's at 2, and we start out with a half. So we need to multiply everything by 4 in order to get the 1/2 to be a 2. And when we multiply the reaction by 4, we also need to multiply the energy, the enthalpy, by 4. Now we look at water. Here we have 6 and we have 2. So we need to multiply by 3 in order to make that a 6. And we also multiply our enthalpy by 3. So once again, we started out with our original equations in the blue. And now what we've done is we have flipped and multiplied down here for our new equations. So we have now 2 nitrogen and 6 water. And what we notice is that we have hydrogen here cancels out. And these cancel because we have hydrogen on the left side of the arrow and the same number of hydrogen on the right side of the arrow. So we can subtract the two, just like if we had a 2x on the left and a 2x on the right. Those two cancel. Now if those two were not equal, we would subtract them. So if say it was 6x on the left and then 2x on the right, in our total we would end up with 4 on the left. So remember, if it's on opposite sides of the arrow, you subtract. And now that we have canceled out what we can, we add up our reaction. So we have our 2 nitrogen and 6 water. That's over here on the reactants. 4 ammonia, 3 oxygen over here on products, which is what we wanted. We have achieved our desired reaction now. We can add our enthalpies. So 1452 plus a negative 184, and we get positive 1268 kilojoules. So here's an example. This is our desired reaction. SO2 plus 1/2 O2 gives us SO3. Do not freak out about the fractions. Our given two reactions are here. S plus O2 gives us SO2, and 2S plus 3O2 yields 2SO3. And each of those has their enthalpies. Now the first thing we can do is we notice SO3 is a product, SO3 is a product. Great, we do not have to flip reaction 2. Now on our desired, SO2 is a reactant, and in reaction 1, SO2 is a product. So what we need to do is flip the first reaction. And when we flip the first one, our energy is now 297 kilojoules. Now we can start looking at our coefficients. SO2 here has a 1, which is a 1, good. But here SO3 has 2, but we need 1. So what we need to do is multiply number 2 by 1/2. And when we do that, we also have to multiply the energy by 1/2. So what we're going to do is we're going to add those two equations now. So it's only going to be S plus 3/2 O2 yields SO3, and we will get our desired reaction. And once we do that, we can then add our energies. So it'll be 297 plus a negative 396, which equals a negative 99 kilojoules. Now, energy in our world, we're going to look specifically at coal. And coal is formed from the remains of plants under high pressure and heat over time. Now, this is the only real one you need to know for the exam. And understand that coal has large numbers of carbon, and it's the solid. We can get liquid, obviously our petroleum, and we can also get gas, our natural gas. But coal here is from the remains of plants under high pressure and heat over time.